job done something. Which like software do we should we use, like Houdini or in Maya or some?
I'm not 100% sure what is the best way. To be honest, I've never done it. I don't know. I know Maya can be helpful on that. I know Unity to a certain degree could do some of those stuff. I think since you're talking about air situation, ask the hybrid team, the air hybrid, no, hybrid air, sorry, okay, from last year. And ask them, because they did a lot of those things. They may direct you, to what you should be looking at.
Yeah, okay.
Tell them what you're trying to do, and they may be helpful.
Okay, thank you.
No worries. So we do water?
Yeah. Daphne, can you share your screen?
Yep. Sorry, sharing.
Daphne, any troubles with the snow? You're from Athens, no?
Yeah.
Did you have electricity or something? All good?
Yeah, we had some blackouts. Okay. Yeah, we had big issues with I don't know what's so little.
No. Yeah.
Yeah. Anyway, Greece is running many political issues right now also.
Yeah, I know. There's a lot of turbulence.
Yeah. It's not very nice, the situation. Anyway, so yeah, we are water team. We started to focusing on our research and studying the computational part. So we will quickly go through these first things. As we said, the amount of fresh water is something very important that we could study and that we should have in mind for the conceptual part. And then we wanted to focus the water in terms of the water phenomena. So as an abstraction, we can see here the different water formations that we can see around us, very common. So we could question ourselves, what is the formation rule set for each one of them, which is a formation factor, and which could be a formation simulation method. So we go from the smaller scale to the larger scale. And we just keep that in mind, but we are not sure that we can approach that in the computational part directly right now. So we had to, we discussed that with Mostafa. Mostafa was suggesting more to focus on a molecular scale and to start studying that part. So we just go through this phase chains. We saw that the most important behavior of water is actually phase changing. Yeah. So we wanted to focus on that part. There are also a couple of interesting behaviors that we have a diagram here, like instant changing, volume expansion, snow crystal spikes, bending, thickness, surface tension, capillary action. But we were thinking that it would be interesting to try to find ways to also simulate these things. So we can go through, I skip this part, and so regarding the computational strategies, we were thinking that we could think of water as a material. Water as material, which includes phase changing and basic water behaviors. And we could think of how to simulate the water as a material, how to create a digital material, and to augment these behaviors. This could be the strategy number one. Another strategy could be to focus on the way that water interacts. So this could lead us to a strategy of fluid dynamic simulations, where we should take into account variables like incompressibility, pressure, flow, velocity, things like that. So, and then a third category, a third strategy could be water as a container. So as we know, water contains, always contains, it contains minerals, sediments, microorganisms, planktons, when we're talking about sea. So this strategy could be like a combination. I think we could imagine that as a combination of strategy 1 and strategy 2. So that would provide us with a way to use this life somehow in the conceptual part. So, but for now, we decided that we should focus on the first strategy, which is water as material, and it's the easiest way to think about the computational part for the beginning, at least.
Yes.
So for the first week, we started experimenting with a couple different environments and softwares in order to become more familiar with the different scales that we could address through these different environments. But after these explorations, we decided that we should focus on Maya and Unity to focus on the molecular scale. Maya is an engine that we could use only as an abstraction, but I don't know, unfortunately, maybe for me, because I'm not good at coding, we should focus on Unity. Now to look at further the phase change simulation. So this is the abstraction that we tried to make at Maya for the different phases. It's not really successful, but we tried to understand the different forces of attraction and repulsion between the particles. And in the beginning. So,
but the particles, well, if you go to the molecular scale, they are interconnected, right?
Yeah.
So it's like each water molecule, let's say, is going to have 3 oxygen.
3?
Each molecule has 3 particles.
Yeah.
It's like 2 oxygen. Sorry,
Yeah.
1 oxygen, 2.
No, 2 hydrogen, 1 oxygen.
Yes.
Yeah,
and
it's a triangle.
So
the binding
they
process is.
Yeah, the particles together, they are interconnected somehow.
Yeah, but we are now simulating an abstract way.
Yeah, exactly. That's my point, that we are kind of struggling there. Because, repulsion and attraction is a property of particles, but not necessarily applying to what you're doing.
Yeah, and Mustafa said it's similar when we consider into a molecular scale or a water scale. The abstract way is similar.
Yeah, because when the phase change, like from solid to liquid, the molecular bondings is also changed, like two atom well, like stick.
Yeah. Agreed.
Yeah, but this is not atoms. This could be molecules. The bonds between the molecules.
Yes.
So yeah, for example, solid is not at all a successful example, but maybe liquid could be a more successful. Like we wanted just to represent the how close or how.
Yeah, they are similar. They're not that. It's not bad. It's not completely off. I think it's relatively close to what you need to achieve. And I think it demonstrates the point that the air is much more dispersed. The ice is, let's say, closer. The liquid is the closest they can get.
Yeah, exactly.
So yes, some rough simulations of a phase change, let's say. So how that ice turns into water, blah, blah. And again, and very abstract. We started thinking whether we should introduce growth in these simulations, just to show, because crystallization is a very different process, but this could be very confusing, so we left that part. After the discussion with Mustafa last week, we decided that he suggested that the flocking analogy, the flocking simulation, could help us to understand or to represent the liquid, the fluid. So this is an abstraction of how flocking simulation works and the basic rule set of behaviors, which is separation, cohesion, and alignment. We were trying to think in an analogy how we could relate fluid with phase chains of water. So this slide tries to depict that with the use of a target.
Yeah.
But it's again a very rough analogy. And then we try to be more specific and set and try to find our rule set. So this is the basic rule set for the flocking, and we start from the observation radius. Speed is something that we should control, and then the direction of its molecule, which consists of repulsion, forces of repulsion, attraction, and cohesion.
Question: is there repulsion? Because I have a feeling there is no repulsion. There is attraction. Well, there is repulsion to a certain degree to, let's say, two molecules coming together but not getting squashed in between. But generally in water, I think there's only attraction. So the molecules, they come together and they stay there. And they separate only because this attraction is relatively weak. I don't think there is repulsion as such. I think there is repulsion to, let's say, the radius, to the diameter of, actually to the perimeter of its mole. So they just come together and they get stacked, I think.
But if it don't have a repulsion, then they could be overlap to each other.
Yeah. If there is repulsion till they overlap, but no more than that. If they just touch, they shouldn't be repulsing each other. They should just stay there.
Okay. So
I think
it doesn't have a force.
Yeah, exactly. I don't think it's very
have a like collide to make them don't overlap together.
Exactly.
Okay.
Yeah. So this is how we could imagine each phase. We tried to find in which how much speed or how the values of each one of these variables that each phase should have.
So which phase is that? Is it starting from solid to air?
Yeah, this could be solid, which we could say that it has very low speed. The molecules are very slow. They have high attraction, high cohesion, probably quite high, not exactly, not totally cohesive, and small observation radius. After that, liquid could be, we could advocate that it has medium speed and medium attraction, low cohesion, and small observation radius. And air, we could say that it has high speed, low attraction, low cohesion, and big observation radius.
Now, on that, yeah, I'm a bit skeptical about this flocking behavior, because a solid, it has zero probably cohesion, and zero, like some of the values are actually zero because it's really not moving. And then there's a massive issue of viscosity in the liquid part. I don't know how much in water, how much it changes depending on temperature. let's say a very cold water with a very warm water, does it have a viscosity difference?
Yeah, density changes. Yeah.
Yeah, there should be something, not dramatic as much as, let's say, oil, but there should be some change there. And then that could be simulated, perhaps.
Temperature is definitely a variable that we should introduce.
Yeah.
This is actually what we say here, that the steps could be run firstly the simulation by changing these initial variables that we set here, play the variables to succeed phase changing, and then introduce the temperature as a variable in a particle.
Yeah.
Then we should go further and introduce scale and environmental factors to succeed this phenomena that we called before. And the goal, I'm not sure about that at all, but the goal is to produce a computational system that has a clear rule set of the phase changing.
Mm-hmm.
But we are also skeptical about how flocking, because we are still struggling with this coding part, which we'll present right now. But so we are not sure how successful it will be, and also in the solid state phase.
It could be, I think it's an exploration. You need to do effectively, you want to simulate the behavior of water and when it phase changes, right? So it's not the traditional flocking as you had in the first simulation where there's a tractor moving and the water is following. This is not going to take you anywhere, but it's more about how how the molecules actually influence each other while you're changing the parameters within the system. And there may be a bit of flocking because there will be some movement when there is phase changing in the molecules. There will be movement that actually affects the system. So when you freeze something, the molecules will push away other molecules. Now, if you have, let's say, a grid setup, and you say freeze it and then defreeze it, and what's going to change? Maybe it's not as interesting. But if you start freezing and hitting other parts of your system, you may start getting this kind of forces which they sculpt the water itself. And actually there's this kind of a design game of how you can actually control this behavior to generate form, let's call it, for now. It doesn't matter what it is. Generate some pattern.
This was what we could imagine also, yeah.
I think that's where you are. What you should be looking at.
That's why we mentioned also the basic behaviors, because there are some behaviors that look like sculpting. So if we could find what is it, we know what makes this behavior happen.
Yeah.
So this is something that adds to this.
I think the setup of your flocking is what is important. You shouldn't think about what it is normally used as a flocking behavior. It's more, it needs to be quite set for your case.
Yeah, we talked that with this. Is it clear? Is it, because, for example, we discussed that alignment is not important for us. So these are only the important features from the flocking behavior.
Well, you will need to have some alignment.
Sorry?
You will need to have some alignment factor. Because once they start moving, they will need to align somehow to... it's not a very important one, but I think it will be. You need to have it as a factor. I mean, it's...
You mean they are not moving in a random way?
Yeah. That's what alignment does. You kind of point the vectors towards the same direction. So, you know, when a molecule is touching another molecule and you move the molecule, somehow it drags the next one. So in computation, you kind of need to tell the computer that those two, they need to kind of go together. Not exactly, but kind of. So you will need to have it there. Yeah.
Yeah, I get what you mean. Just
but I think, let's say, the speed is something we wouldn't be caring much, because, well, except there may be some force generation, but it's not something you really need to consider, I think. I think repulsion and attraction, repulsion less, it's, I think, the safe boundary of how the molecules stay together. The attraction is important. It's going to play the role of growing. The cohesion as well, I think it's, and then all those, they will be affected by the temperature. And then once you talk about the environment, I think the pressure is also very important. The environment pressure, because that changes completely how it behaves as a system. I know it's tricky at the moment, but I think it's quite interesting. And then, you know, as you said earlier, water is a container. Whatever it contains within it actually changes all those properties. You know, the boiling points and stuff like that. All these are, and the freezing points. So, I mean, this is another parameter, but let's don't get too complicated. I think temperature is the starting point.
Yeah. So we should set a set of values for its phase and make it clear. We could, by coloring its state, we should make clear the phase changing process. And then we go deeper, more in depth with blocking simulation. Yuji?
Yeah. Here is the next. Here is we do some simulation on boys to try the cohesion force and the separation force, because we thought we don't gonna use alignment force, so I didn't attach a alignment force to it. And next slide. And this I think you can go to 51.
Yeah, but you see here, those simulations, they are a bit too floating behavior simulations, and that's where actually it doesn't help you. You move something and then everything kind of follows.
Yeah.
I don't think this is your case.
We should have a container. How we should do that?
I think it's kind of a container with molecules, and then trying to differentiate conditions within it to change some of the properties of the molecules and how they connect to each other. So some molecules will come closer and kind of, let's say when they are in the ice formation, they come actually in the ice. I don't know if they're coming closer or getting further apart, but the bonds are stronger. And then when they go to the liquid formation, it's much looser. So it's kind of this system trying to maintain balance in between it. You may not get something very visible. That's the problem. But I think it's a starting point.
Yeah. Okay.
You know, when you freeze water, it gets bigger, right? So this is the extreme behavior of one side, and then when you boil it, it actually disappears. So in between those two states, the molecules behave completely different. So I think it's kind of what you have here. To a certain degree.
It's like 3D grid, the container you said. Is it? I
think you start from there somehow. That's the starting point, and then I think by changing the locally the conditions of temperature and the behavior of each of those molecules, then it may start giving you something else. I mean, it is a tricky problem I think you need to increase your population as well.
Yeah, sure. Next slide, 53.
But start also getting a container and go through the phase changing all together. Like, what if you freeze it? How do you simulate freezing of a container of water? What is going to happen? Effectively, try to think of it. Just get a box, fill it with water, put it in the freezer. What's going to happen? It's going to start increasing the volume and then start dripping out, right? Can you start simulating that? That's going to give you the first, let's say, direction that things are simulated in the right way.
Yeah.
So start from the extreme scenarios, and then you can start mixing and trying to control your system.
Apple, do you think if I froze the water, then the population would be growth, or it stays
No,
the
there's
same?
no growth. There's no growth in water. I mean, effectively, you start from the same number. You don't have growth. It's not a growth system. It's the same number. It's the distance between the molecules and the size of the molecules, perhaps, and the bonds in between them that actually makes a difference.
Okay.
And that comes from the properties of water, right? It's not.
So
Yeah.
the key is
It's the first part of the research you had.
Yeah. It's same amount of molecule, but it's expand 9% because of the bonding extension.
And now we simulate the particle without it can change the size. Maybe.
Well, I think the size should be changing. I think the molecules get bigger. I'm not 100% sure. I mean, you do the research, you know better than me. And the bonds and the connections are changing. So I think this is the three factors.
Yeah. The molecule gets bigger because the bonds get
they expanded.
Are expanded.
Yeah. But there are bonds between the atoms and there are bonds between the molecules, right?
No, it's only between atoms, and the molecule is attracted by electric pulse.
And that doesn't change.
Yeah, between molecules actually stay the same.
Okay,
but
fine.
But the chemical structure changed because, like ice spike, it's actually combined with 6 molecules. But when it's liquid,
so you see that's where it's getting interesting because that's the level you need to simulate.
Yeah, that's true.
Of it's not one round sphere. It's actually 3 to 6 perhaps.
Yeah.
So the way they are actually changing is that's exactly what you need to focus on.
Yeah.
You mean the exact bonds between molecules? Like we should get groups maybe of molecules.
Maybe we can set how many neighbors it can read, or how many how long the distance it
To
can.
what you said earlier, Yuki, on if there is a growth, I think when there is a phase change, there's a growth in the number of your particles, let's say, that is driven by the phase change. It's not growth by
the neighbor. It's growth by the.
It's not a bacterial growth, right? It's not generating new. It's actually the same, subdivided, changing the geometrical configuration of them, and then they become bigger in volume.
Yeah.
But the mass is the same.
Okay.
Yeah, it grows in terms of phase changing. So more water will turn to ice.
Yeah. So I think that's where the tricky is to get in the very small scale and see what is the changes there and how that affects the bigger population.
Yeah. Okay, go on, Yuji.
Next slide, 53.
I don't remember the numbers.
Just one have a green color and this one. And this is Alex gave us the advice, like you said the one part of area which is frozen and the other part of area which is gas, and maybe they can get some interact in the edge of this.
I'm kind of start changing a bit my opinion on that. I think you should first, as a safe option, go to the extremes, like one container, freeze it, boil it, have it in the standard configuration, see what that phase change is, and then start mixing and matching. because if you don't achieve the first, you won't be able to do the second. It will be guesswork.
Okay.
This density is very important also here to address, maybe.
Yeah. Density is important, of course.
Yeah, density and maybe also grouping of molecules.
Effectively, I think it's the same thing.
Because, for example, no.
It's like still suggest us we should have like 3 different level of simulation. So first is in molecule level, and second should be like organ level, and the third should be like the body level, like the general how ice grows and water like grows like that.
Yeah,
it's gonna be clear. Yeah, we have some later.
Yuji, you wanna speak on that? I think.
This is before we talk with Alex. We do some try on attraction force, but with external targets. It's not particle target itself. Next.
I mean, to a certain degree, all those simulations will be probably more when you talk about the larger scale. When, let's say, there's water flow, then that one could be much more logical. Let's say there is a flowing behavior when you try to simulate the water flow. So maybe it's in another scale, more useful for you. I mean, not that, but
targets could be used in terms of flow, right?
Yeah, I think exactly.
Yeah, we could show also the bending of water, polarity.
Yeah, this can be the next step when we finish the phase changing simulation.
Well, maybe it's in parallel, right? Doesn't need to be
okay,
step by step.
Okay. Yeah, this can be linked to like the ice formation in different direction.
Yeah.
Yeah, next.
For this, actually, is kind of particle-based simulation for fluidity. So it's in Maya, I added gravity and turbulence. So it's like generate 100 particle per second. With this two force, it's actually can say the simulation of the fluidity between particles. Okay. And next.
Well, yeah.
Okay.
The next growth system.
Yeah, and this is based on L system in Maya, and but yesterday with Mustafa, this is maybe not look into this.
Yeah, I agree.
Okay. Yeah.
So again, the steps that we have to follow. And then we thought about a little bit about the touch designer and how we could use that to interact with water. So first, it could be how we mine data from water in terms of environment, how we read ocean data and read that data, how we read water patterns, how we sensor temperature, or how we predict weather, I don't know. And then how we could interact with the user, let's say, or how humans could interact.
Okay, and this simulation is actually, I find quite interesting. It's exactly simulates how a snowflake grows.
Yeah.
Yes, based on touch designer. But in this case, the touch designer simulation in this case is based on seed. but city is like for what I understand, the city is actually pixel. So I'm not so sure how it can actually develop in terms of prototyping for a later stage.
To be honest, I don't think it's Touch Designer. I don't think it's doing the simulation as such. I think it's more visual representation of data. So it's a different field of. It's a different tool. You're not gonna do it. You use it for simulation, but perhaps inputting information from your simulations to it, it may give you the visual result you may want. That's why we want to use it.
Yeah. Okay. Yeah. In terms of large population simulation, I find Touch Designer can be much more efficient.
Could be. If you give it the right data, it could actually help you on that.
But it has no physics, so it's not exactly simulation. It's just.
It's like this simulation is based on points, not particles.
No, I agree. I mean, that's why we're thinking Touch Designer. It comes together with something else. You connect it with something else. Either is, let's say, Arduino to get sensor information in, or another software which actually can interconnect and send information. It should be straightforward.
But I find some interesting part. Maybe it can be used. Because in Touch Designer, each battery inside is actually have some certain code. So if we can transfer the code into Unity, such as, then maybe it's working. But I'm not so sure. I just see these possibilities, but maybe I can look into this.
Yeah. I think, as we said earlier, I think the strategy would be to generate information, generate data. In Unity or Maya, and export it, bring in a Touch Designer, and give it a visual representation. That's kind of, and then whether we can actually feed in information from sensors, that's something also we should be looking at. But step by step, I think start with your simulation, see where we are going with that. I think you have a direction. And let's see how it goes.
Yeah. So we think that the direction is pretty clear, and we.
I think it's clear now how we are gonna convert that to architecture. I don't think it's the time to think about it, but I think it's quite clear.
It's quite scary to simulate a molecular level.
It is true, but it's funny that water is very abstract, and then when you go to molecules, and then it starts getting actually very organized. And that's every material, of course. It's becoming geometrical. It becomes almost like architecture. It's funny. Like you zoom in and you see architecture.
I have one thought about this in terms of urban scale, because like one drop of water is like 1 billion molecule together. But like with the fluidity, it's actually somehow it's kind of alignment can shape the urban organizations.
It could be. Let's don't talk about architecture for the moment, though.
Okay.
I don't want to infect the discussion.
Okay.
But it is it's not frustrating. It's actually, as you say, a bit scary. But I think it's you'll get used to it. Don't be afraid.
No.
Apple, do you think Touch Designer can do something rendering after we have some animation simulation from Unity?
To do something what? Randomly?
Rendering.
Render. To be honest, I have no idea. You know more for Touch Designer than me. I can start having a look actually, but
okay, I share my screen.
I think you can get some nice visual representations, to be honest, because that's what the tool is for.
Yeah, and it can have interaction with music.
Yeah,
and
well, you love music, no? Video with music, yeah.
Oh, can you see my screen? This one,
Yeah.
like if we have particle, if we can don't simulate, just make the trails of the particle moving.
Could be. I don't know. I guess so. I think that's what they're using it for.
Yeah.
All right.
Yeah.
Everybody okay?
Yeah.
Happy? Excited?
Apple, you
Yeah.
look very confusing.
Very confusing.
Yeah, you look
confusing or confused? Why I'm confused? What do you mean? Oh no, we are lost in translation here.
Yeah. Your expression, not very good.
Not very good. Nah, it's always like that. So don't worry. Don't take it for
Okay.
You cannot get expression from me, to be honest. I mean, everybody says that I'm quite flat-faced. I don't laugh. I'm like flat. So you cannot know what I'm thinking. I think that's what people say. I don't know. Maybe the camera is a bit different. Okay.
Okay.
Anything else?
We should just practice this direction of simulation we discussed, and like our goal for the 11th of March could be to succeed at least phase changing and introduce temperature is something as a variable.
You need to
right?
all the teams. You need to introduce a system. You can use a system that you can actually control. And that's the point of each one having a variable, right? You have temperature, the fire team may have heat, but what is the variable that you actually start controlling your system? It's not the only one, but it's an important one. Or the let's say the game of life team, the earth, the bacteria growth and stuff like that. Like everybody has a kind of the main variable that controls the system, and it's all about demonstrating what is your system, what you are working with, and how you start controlling it. And that's why cataloging is important, to start getting an array of data, visualized data, and how your variables affect that.
Yeah, we had issues with setting up the behavior, so we couldn't get a catalog yet.
I think once you do it, though, it's fast, relatively fast, right? The problem is getting the setup right.
Yeah. But I wanted also.
Yeah.
Sorry.
Go.
No, I just wanted to mention that Ula from our team is moving today, so she wasn't able to join the class.
He's moving. Where is he moving?
To London.
Really? Nice. Yeah. Well done. More people need to come here. Yeah. Should we do a drinking session one day, like a going out one?
Yeah.
I think we should organize something like that.
That's nice.
Yeah. Maybe after your presentation. Although it's not the same, but what can we do? I mean, that's where we are.
But yeah, we can do it.
Okay, guys, cool. Have a good Sunday, whatever is left.
Okay.
And if you need anything, let me know. Okay?
Okay.
Thank you.
Bye-bye. See you soon. Thanks a lot.
Thank you.
Well done. Bye-bye.
Bye.